Right now, there is a number dominating AI product announcements: 128,000 tokens, 200,000 tokens, a million tokens. The context window has become the ultimate marketing metric. The pitch is straightforward. A bigger window means the model can hold more, process more, and essentially possess a flawless, infinite memory for whatever you feed it. It feels like we've given these systems a colossal filing cabinet, where every single document, every paragraph, and every line of code is stored with perfect clarity, ready to be pulled the second you ask for it. But in late 2023, Anthropic's own team documented a bizarre failure while developing Claude. They ran a benchmark to test the model's ability to retrieve a specific sentence buried deep inside a massive 200,000 token context window. The information was right there in the prompt. The model had complete access to it, yet the retrieval accuracy was just 27%. That failure reveals a deep architectural quirk. A context window isn't a neutral storage drive where all data is equally accessible. It behaves more like a spotlight. It illuminates some parts of your prompt brightly, leaving a massive blind spot everywhere else. There is a full breakdown of the math and research behind this in my Medium article, linked in the description below. But right now, we are going to map exactly what that blind spot looks like. Treating an AI's context window like a perfect memory bank relies on a false premise. The system is structurally incapable of weighing all the information you give it equally. To see why, we have to look at the attention mechanism. Large language models don't have memory in a human sense. They process text by allowing each word or token to query other tokens and assign them a weight of importance. And that weighting process is dictated heavily by where a word physically sits in the sequence. Because of how information is routed across the neural network's layers, the beginning and the end of your prompt receive intense focus. The middle, however, is systematically starved of attention. This animated diagram maps exactly how that focus is distributed. On the y-axis, we have attention weight, and on the x-axis, the physical position in the prompt. Notice the distinct U-shape. The attention peaks at the very beginning and the very end of the text, but drops into a deep valley right in the center. Now look at what happens when we add erratic static to that valley. This represents the distractor problem. If you fill a prompt with text that is somewhat related to your query, but doesn't actually contain the answer, that extra text doesn't just sit there quietly. It actively competes for the model's already depleted attention. This acts as a severe tax on the AI's reasoning capacity. A crucial fact buried in the middle of a document is hit twice. First, by the positional disadvantage of being in the center, and second, by the semantic competition from the surrounding noise. Researchers call this the lost in the middle problem. It is a geometric property of how transformer architecture reads text, meaning the center of any long prompt is an inherently dangerous place to put critical instructions. The effect itself is heavily documented across different AI models and tasks, but the exact mechanical trigger inside the architecture, whether it's causal masking, residual connections, or something else entirely, is still an active debate in computer science. A team led by researcher Nelson Yu ran an experiment to see if the AI was trained to favor the edges during its instruction tuning phase. They tested a fully tuned model against its raw base version. Both produced the exact same U-shaped curve, ruling out instruction tuning as the root cause, which brings us back to Anthropic's benchmark. The engineering team managed to fix Claude's 27% failure rate without changing the length of the prompt. They simply added one line of text at the very end. Here is the most relevant sentence in the context. Immediately, the model's retrieval accuracy jumped to 98%. The AI didn't suddenly get smarter. The target sentence was always there, but that new instruction acted as an attentional anchor. Placed at the very end, a structurally privileged position, it redirected the model's spotlight right to the correct area before generation began. An AI's reading comprehension is strictly dictated by these structural cues. Prompt engineering requires careful geometry. What information you provide is only half the battle. Where you position it determines if the model actually sees it. The sheer size of a context window is an availability metric. It tells you how much data the model can look at. It is not a reliability metric. It tells you nothing about how accurately the AI will weigh the information you care about. Bumping a model up to a 1 million token limit doesn't solve the issue. A larger window doesn't flatten the attention curve, it just stretches it out. The middle of a massive context is often worse off than the middle of a smaller one. This architectural constraint means the ordering and density of your information matters significantly more than the raw volume. A tight, carefully ordered prompt with genuine relevance will easily outperform a massive context window, padded with related but unessential noise. In the next episode, we will explore exactly what this positional bias means for retrieval augmented generation, or RAG pipelines, and why most enterprise AI systems are currently solving the wrong half of the problem. If you want a deeper dive into the mechanics of positional bias, check out the full breakdown in my Medium article linked below. Before you write your next prompt, take a look at your templates. Check your non-negotiable constraints. Are they sitting at the very end where the AI is guaranteed to see them? Or are they lost in the middle?